Hello, this is the second of our two videos on t-tests. In the last one we looked at the paired sample t-test, which is the t-test that you do when your data come in pairs and when you're looking at the mean difference between the data points in those pairs. The two-sample t-test is one where you have two groups of data which are all independent measures and you want to compare the means between those two groups. So with the paired sample t-test you're looking at the mean difference. With the two-sample t-test, you're looking at the differences or the difference between the means. Let's start by looking at the kind of experiment that might give you data that you would analyse with a two-sample t-test. So let's say, for our example, that you're interested in whether a heat shock improves the resistance of plants to a fungal pathogen. And you're working with bean plants. So what you might do is take 20 seedling bean plants, assign each one to either a control or a treatment group. The controls then don't get a heat shock, the treatment ones do get a heat shock. Each plant in both the control and the treatment groups is then exposed to our fungal pathogen, and we leave them to grow for 3 weeks. And at the end of 3 weeks we harvest them and we measure their leaf mass. So we're getting an indication of how well they've grown despite being exposed to this fungal pathogen. This is giving us data where the data points are not paired like they were in the previous example. Here each seedling is hopefully an independent measure of the effect or not of getting a heat shock on plant growth when they're exposed to the pathogen. Let's just look at these data. So here are our control and treatment values, and these are the leaf masses of our plants in grams. We can calculate the mean for our control group and the standard deviation. The mean is 12.08, and then we can do the same for our treatment group. And you can see that the mean for our treatment group is somewhat higher than the mean for our control group. So on average, our treatment plants have more leaf mass than our control plants. Let's visualize this with a box plot just to make sure that our data are well behaved. And you can see that, again, the treatment plants seem to be largely heavier than the control plants. You can see that the interquartile range for the treatment plants doesn't even overlap with the interquartile range for the controls. And that's quite encouraging. That's suggesting that there's a reasonably strong pattern in these data. Nonetheless, there is some overlap. We've got some control plants that were quite heavy, and we've got some treatment plants that would have been below the interquartile range for the controls. So we're not sure that this pattern that we're seeing, where the treatment plants are heavier than the control plants, is a consequence of sampling error, or whether the pattern that we're seeing is unlikely to be a consequence of sampling error. Do we just have heavier plants in our treatment group because we happen to get them as a result of random chance, or is that actually very unlikely, and is it much more likely that what we're seeing is a real effect? We can maybe get a bit more insight by plotting the means and the confidence intervals. If you remember, if confidence intervals don't overlap for two means, then that, as a rule of thumb, is an indication that those two means are significantly different. Here are the confidence intervals for our two groups plotted, and you can see that these are in that annoying zone where the confidence intervals do overlap, but they don't overlap a huge amount, and that means that there might be a significant difference between the means, or there might not, and we can't tell just by looking at the confidence intervals. So even though we've visualized our data and we've looked at the confidence intervals for each mean, we still don't have a good feeling as to how confident we can be that the difference that we've seen between these means is not a consequence just of sampling error. So what can we do? Well, we can do, unsurprisingly given the title of this video, we can do a two-sample t-test to find out the answer. What we do with a two-sample t-test is we start out by calculating the effect size, and the effect size is simply the mean of one group minus the mean of the other group. So the difference between our two means is 2.67. It doesn't actually matter which one we subtract from which other one, but we know that the difference between the two means is that value. And then, having calculated that effect size, what we want to do is somehow standardize it so that it falls on a statistical distribution that will allow us to assess how likely we would be to see that effect size were the null hypothesis true. So the way we calculate that for a two-sample t-test is by using this formula. This is actually the formula for a two-sample t-test where the sample sizes are different. There is a somewhat simpler formula for one where the sample sizes are the same. I'm using the more complicated one here because that's the one that you're going to be using more often than the formula where the sample sizes are the same. So we have the effect size, the mean of one group minus the mean of the other group, and that's then divided by something called SP multiplied by the square root of 1 over the sample size of one group plus 1 over the sample size of the other group. What is SP? Well, SP is something called the pooled standard deviation. It's an estimate of the overall standard deviation for both groups, and it's weighted by the sample size of each group. So if you were to take the average distance from the mean for both groups and weight it by the sample size, that gives you the pooled standard deviation. It's best to think of it really as just being an estimate of the standard deviation for both groups. The formula for calculating it is quite intimidating, although there is method to the madness, and if you look at it, you can make some sense of it. So you're looking at the variance of both groups adjusted by the sample size for both groups, divided by the degrees of freedom for both groups, which is n1 plus n2 minus 2, because we've calculated two means, and then the square root of the whole lot. So that is related to things like the formula for variance. But don't worry about it too much. You don't really need to know that to do a t-test or to interpret a t-test. I'm just showing it to you so that you understand where all these numbers come from. If we plug the numbers that we've already calculated for our samples into that formula, we get a pooled standard deviation of 2.102, and we can then plug that back into our formula for t, and what we get is that t is equal to 2.67 divided by 0.94, and that means that t, our test statistic, is equal to 2.84. So we know that our test statistic t is equal to 2.84. We know that were the null hypothesis true, that value would be distributed on a t-distribution, and that would be a t-distribution on 18 degrees of freedom. Once again, it's n1 plus n2 minus 2, and that's because we've estimated two means, so we take 2 off our sample size, our total sample size, to give us the degrees of freedom. So what does a t-distribution on 18 degrees of freedom look like, and where would our t-value go into it? Well, this is the t-distribution on 18 degrees of freedom, and I've plotted the areas under that curve where you'd expect to get 2/3 of all the values, where you'd expect to get 95% of all the values, and where you'd expect to get 99% of all the values. And we can draw in where our value of 2.84 would be, and you can see that our value of 2.84 is outside the part of the t-distribution where we would expect to find it 95% of the time. So that's telling us that we have a statistically significant difference between our means. We can calculate a more precise probability of observing this value or a bigger one by plugging it into R, and we get a p-value of 0.01. So what that's telling us is that were the null hypothesis true, were the population means of our two samples actually the same, we would only find a difference as big or bigger than the one we found 1% of the time. And we would interpret that and say that we have a statistically significant difference between our means. And I've written this out formally here, just so that you can see what it looks like when you do that. We wouldn't normally write something like this down in, say, a scientific paper, but that's actually what the sort of formal definition of significantly different is. So the probability of observing a difference as large as or larger than 2.67 is roughly equal to 0.01, and that means that we would say we have a statistically significant difference between our means. Okay, most of the time we don't want to be doing things like calculating pooled standard deviations by hand. So what we're going to do is we're going to get a computer to do our t-tests for us. In R, if you're going to do a t-test, if you're going to do a two-sample t-test, you want to have one variable, which is your response variable, and a second factor, which is your grouping variable. and then you put it into the ttest function like this. So we have the ttest function, then we have response, then we have the tilde, which means the thing on the left as explained by the thing on the right, and then we have our grouping variable. And if we were to do this, we get the results of a t-test. Here's one example where I've done something slightly different just to show you that the numbers we get are the same as the numbers we got when we calculated our t-test the long way beforehand. So this is the output from a t-test done in R on the data that we've been looking at. The only thing that's slightly different from what I've just told you is that I've added an extra argument here, which is var.equal equals true. And if you're doing a two-sample t-test and you want the classic two-sample t-test, you have to tell it this. What it's saying is that the variances of the two groups are equal or roughly equal, so we don't need to worry about that. One of the big assumptions of a t-test is that the variances of the groups you're looking at are the same. Quite a lot of the time that's not the case, and the next example I'll show you of doing a t-test in R takes that into account. But this example here with the argument var.equal equals true is the classic two-sample t-test, and what you can see is that the numbers here, give or take a little bit of rounding error, are the same as the ones we just calculated. We've got a t-statistic of 2.84. One thing you might notice is that this is actually minus 2.84. That's simply because R calculated it the other way round from the way we calculated it. It doesn't make any difference which mean you subtract from which other mean, you'll get the same result. So t is 2.84, 18 degrees of freedom, and our p-value is 0.01, just the same as we just calculated. The other thing that R gives you, which is useful, is a 95% confidence interval on the difference between the means. So rather than the 95% confidence intervals of the means, which we looked at earlier, this is the 95% confidence interval for the difference between the means. So what's the confidence interval on the actual effect size? So we can say that when our plants are given a heat shock and then exposed to a fungal pathogen, their weight is going to be somewhere between 0.7 and 4.65 grams heavier after 3 weeks than plants that weren't given a heat shock and exposed to that fungal pathogen. Finally, let's see what we get if we do this calculation without setting var.equal equals true for our t-test function in R. This is what we get, and you can see it's slightly different. This is now called a Welch two-sample t-test, and this is an adaptation of the t-test that works when you have different variances between groups. Our value for t is basically the same, although in fact it's calculated in a slightly different way for the Welch two-sample t-test. And the other thing you can notice is that the degrees of freedom are fractional. And one thing that the Welch two-sample t-test does is it adjusts the degrees of freedom according to the difference between variances. So if you had a big difference between variances, we'd expect to see degrees of freedom that were quite a lot lower than the ones for the standard two-sample t-test. In this case, the variances are basically the same, and so the degrees of freedom are almost 18 for this one. And then finally, you can see the p-value is almost exactly the same as the one that we calculated before. Which one should you use? I think that unless you've got a good reason not to use it, you should probably use the Welch two-sample t-test. If you're doing a t-test in R, you're never going to get groups that have the exact same variance, and this is just going to give you a slightly more accurate p-value than the standard two-sample t-test will. Okay, thank you.